Okay, we are on to 2B.4, part 3, defining the inverse functions. Okay, so on part 3, we are still diving into inverse, and we've already talked about that meant switching our input and our output. We talked about that for notation. We are writing it with f to the negative 1. Okay, what's new here is applying composition to verify that two functions are inverses of each other. And so when we are applying composition, that means that I'm putting my inverse function into my original function, and it has to equal x. And I also have to put my original function into what I think the inverse is, and it has to equal x. If both of these are true, then it is an inverse. The two functions have an inverse relationship. Okay, how do we find an inverse of a function algebraically? Well, first, we're going to replace the function notation. If it's written with f of x with y, we're going to switch our x and y variables. So we're going to switch x and y variables. We're going to solve for y, which means that we're going to isolate our y again. Once your y is isolate, we're going to replace y with inverse notation of f to the negative 1 of x, okay? And then we'll only do this if the inverse creates an inverse function. So starting off fairly simple, we have y equals 4x plus 8, okay? So the first thing it says for us to do is to make sure that we are in y form, check. Second thing it tells us to do is to switch our y and our x. So we get x equals 4y plus 8. After we switch our y and our x, we're now going to use inverse operations to get y by itself. So the first inverse operation here is going to be to subtract 8 from both sides. We're left with x minus 8 equals 4y. Y is still not by itself, so I'm going to divide by 4, divide by 4, and now we've gotten y by itself. So y is now by itself, and we get y equals x over 4 minus 2. Why is that? X over 4 doesn't simplify, but 8 over 4 does, down to 2. Okay, so now y is by itself. Once y is by itself, it says that we're going to, we're now going to change our y to the inverse. So that's going to become the inverse of x equals x over 4 minus 2. And that is our inverse. Our inverse is a function. Yes, it's a function. And the domain of this function, since it's linear, is going to be from negative infinity to positive. Okay. Up next, we have our quadratic model example here. We have y equals 2x squared minus 6. Again, you want to make sure that you have y instead of f of x. After that, step 2 is we want to switch our y and our x. So we're going to switch our y and our x, and we get x equals 2y squared minus 6. The third step here is to get y by itself. So what are the steps I'm going to take to get y by itself? I'm going to add 6, and I get x plus 6 equals 2y squared. Divide by 2, divide by 2, divide by 2, and I'm left with, I'm going to come over here, we're left with x over 2 plus 3 equals y squared. Last thing I need to do is divide by, I'm going to take the square root of this entire side. So we're left with y equals plus or minus the square root of x over 2 plus 3. Notice that I had to put this plus or minus piece here. I didn't mean to circle it. I should have highlighted it. This plus or minus piece. And that plus or minus piece is our key to let us know that our inverse is not a function. So step 4 is to write this as an inverse if it was an inverse. Our inverse is not a function. So we're going to just write as this is the inverse of said equation. It's going to be plus or minus. And you see how I'm being smooth. The square root of x over 2 plus 3. And it is not a function. It's not a function. In order for it to be a function, we would need to restrict the domain. All right. Here we have 2 to the x plus 4. Okay. 2 to the x plus 4. And I'm going to pause and let you do it because 2 to the x plus 4 is using our exponential and log rules that we've been working on. So we're going to pause and we're going to see how far you all get. Okay, welcome back. So step 1 is to make sure that we are in y equals instead of f of x, which we are. Step 2 is to switch our x and y. So I'm switching y with x, so it becomes x equals 2 to the y plus 4. Next job is to get y by itself. So we're subtracting 4, and we're down to x minus 4 equals 2 to the y. Exponentials are different. Exponentials are different because, sorry, I didn't write 3. Exponentials are different in the sense that once we get here, we now have to use the log. We're taking the log of both sides. We're going to take the log of the same base of our exponent. So we have the log base 2 of x minus 4 equals log base 2 of 2 to the y. Remember, us taking that log is going to cancel out, well, our exponent. And we're setting our power free. So we're left with log base 2 of x minus 4 equals y, which means our inverse function is this log function, log base 2 of x minus 4. Okay, we're going to graph them in the handheld, and you can create a sketch in your notes for you to remember and look at, but I want us to graph in the handheld. So I'm going to open my handheld. I'm using my TI-84 just because it's easier to keep on screen, but you would graph it the same in Desmos. Okay, so I'm going to turn on my calculator, go to y equals, hit clear, and I'm actually going to have it graph the y equals x line first so that you can see it. So I'm going to put in x, and this is, little extra features of 84. I'm going to make it dashed so that you can see the difference. All right, now I'm going to put in my second equation, my actual equation, which is going to be 2 to the x, 2 to the x plus 4. And then I'm going to put in log base 2. Remember, alpha window 5, so I can do log base 2 of x minus 4. Putting that in. I'm going to let Sylvie do her job. So I'm going to hit graph. She's going to draw in my y equals x line. And then here's my exponential coming in. And then she's thinking. And bam, here is my log function coming in. On the log, this is going down, 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 down. You just don't see it because it's getting so tiny that Sylvie can only do so much with what she has. So this would be my graph that I would sketch, or I could have to model what's taking place. If you need some particular points, you could go to the graph and go to the table and look at values, and you can see what I said when I was saying that we have our asymptotes in place, which stops us, and then let me go over here so you can see for x's, you can notice that it keeps going and going and going and going and going. All right. So knowing what I know now, I know that for here, I have a boundary for 4. 1, 2, 3, 4. I went wrong. I can count y'all. 1, 2, 3, 4. I went down instead of up, and I have no clue why. And I'm going to go through 5. And essentially, let me draw in my dash line. So we have pew, 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 2, 2, 2, 2, 2, 2, 2, 2. I'm going to erase this guy. He doesn't belong there. All right. And so my graph was doing something like this. I just got to make sure I go through this. And she was curving on it, not drawing to complete scale. Okay. So this was my Y. Now I'm going to do my inverse function. My inverse had a stopping boundary at positive 4. So 1, 2, 3, 4. So it has its boundary line here. And it was crossing at 5. So it was doing something of the nature of doom, 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 doom. And then continuing out that way. And that is my inverse. Okay. You can look and see more detailed values. Is the relation a function? I don't know why I wrote in a function. Is the relation a function? And the answer is yes. So my first one is an exponential. Is the inverse a function? And the answer is yes, it's a log function. And there we go. Okay. There are two ways to determine if two functions are inverses of each other, graphically and algebraically. Okay. When you're looking at it graphically, you would graph both functions and you would graph to see if they are reflections across the x-axis. Okay. So if we do it graphically, you're looking for reflection across the y equals x line. And if they are, then they are inverse. So as you can see here, these two are reflections across the y equals x-axis. And so therefore, this is a model of two inverses, okay? So we can call this y, and then this is y to the negative 1. So that's how you tell graphically. All right, so if we were to graph these two equations, what do we have? Are they going to be inverses of each other? Are they going to be reflections across? Well, let's quickly graph. These are two linear equations, so they're fairly easy for us to graph. So we're going to go to 2, 1, 2. Our slope is 1 over 3, so we are going up and to the right. Go up, to the right, up, to the right, up, to the right. Then we're going to go down and left, fall and crawl, fall and crawl. And we are all pretty much professionals at, graph linear equations. So we should be able to do a linear equation by hand. All right, so this is f of x. F of x has been drawn. Now we're going to do g of x. So g of x, we're going to go to negative 2, 1, 2. And this time our slope is 3 over 1. So we're going up and to the right 1. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 and over 1. We're going to repeat. 1, 2, 3 and over 1. 1, 2, 3 and over 1. And I can't go any further. So I'm going to do my very best to draw this very steep line. Okay. I'm then going to put in my y equals x line. Okay. So now that I look at it, I'm like, okay, are these inverses of each other? Graphically, I'm looking, they are not a reflection over the y equals x line. If they were a reflection over the y equals x line, then their intersection would have taken place on the y equals x line. They did not intersect on the y equals x line. So therefore, they are not inverses of each other. Let me write this as g of x. So we know that f of x and g of x are not inverses. Womp, womp, womp. Okay. All right. Now, composition. Composition is the other way. That is how we're showing algebraically whether two functions are inverses. Remember, composition is where we're substituting one function into another function and then simplifying. Okay. So we're going to look at this pair of algebra functions. And we're going to determine if it is inverses or not. So we have f of x equals 2x plus 4, and we have g of x equals 1/2 x minus 2. So we're going to split so I can have room. We're going to do f composed of g of x first, which means I'm doing f composed of 1/2 x minus 2. So everywhere there's x, it's going to become 1/2 x minus 2. So that's going to give me 2 times 1/2 x minus 2 plus 4. I'm going to distribute, and that gives me half of 2 is 1. 2 times -2 is -4, plus 4. -4 plus 4 is 0, and I'm left with x. So f composed of g of x works. Now I'm going to do g composed of f of x, which means whatever f of x is, which is 2x plus 4, I'm substituting this into x of g of x. So that gives me 1/2 times 2x plus 4 minus 2. 1/2 of 2 is 1. 1/2 of 4 is 2. Bring down my minus 2. I have a positive 2 and a negative 2. They equal 0, and I'm left with x. Because both of these equal x, we can then say that f of x and g of x are inverses. And that is how you show algebraically that they are inverses. All right. So this time we have logs, which is what we're focusing on and working with. And we're going to do the same thing. Just because it's not a linear doesn't mean anything changes. You're still going to find f of g of x and g of f of x. Okay. So starting with f of g of x, we have f of, I need my log. F of g of x is going to equal f composed of log base 2 of x minus 1. So where x is, it becomes log base 2. So that gives us 2 to the log base 2 of x minus 1 plus 1. As we've learned, if the base of the exponent and the base of the log are the same, they are inverse operations of each other, so they cancel each other out, and we're setting our power free. So we have x minus 1 plus 1. -1 plus 1 is 0, so we're left with x. Now we're going to do the same thing on this side, but with g of f of x, which means g of 2 to the x plus 1. Substituting in for x, so we're left with log base 2 of 2 to the x plus 1 minus 1. PEMDAS told us we deal with our parentheses first. Inside of our parentheses, we have a positive 1 and a negative 1. That equals 0. So we're left with log base 2 of 2 to the x. The base of the exponent and the base of the log are the same. They're going to cancel each other out. Our power is set free, and we're left with just x. Because we have x on both sides, we can then say that f of x and g of x are inverses. Ta-da! All right, and that is the end.